Let me share the screen. So thank you all for signing on. It'll be good to kind of speak to you today about this seminar talk. And I hope everyone's kind of safe and well, and they're all being able to kind of get on to as much as possible, really. But I just wanted to give a little bit of background about myself before I kick on with the talk. So my name is Matt. I'm a second-year PhD student, wonderfully supervised by Raf, Joanna, and Yuri at CEP. And a little bit of background about me. I did a BSc in physics at Durham University a number of years ago now, and a master's here at Imperial in the Sustainable Energy Futures program. And I've seen that Mark Workman is on, and he was my supervisor on that master's program. So hi, Mark. And in the intervening years, that was a few years ago, I worked for a clean tech startup that basically was involved in developing new technology around air quality. And then I joined CEP, and I'm two-ish years in to the PhD. So without further ado, I'd like to give a brief seminar today about a project that was a collaborative study between Imperial CEP and EASA, and more on EASA a bit later, entitled Energy and Nutrition Impacts of Grain Supply Losses in India. And just a bit of a kind of a health check. If anyone can't really hear me or anything like that, please do speak up. But if you want to ask questions or comment or feedback, if you chuck them into the chat, and we'll go through them at the end. Cool. So the headline motivation for this is that we all know we need to feed the world. There's a growing population. Instances of malnutrition are flat or indeed increasing. But we also know we've got this dual issue of achieving the fairly aggressive climate goals, while also sustainable development goals. So how do we do that? Well, part of that, a good start to make would be able to address food loss and waste. So a few of you may have seen this statistic, but essentially approximately a third of all food produced every year that is intended for human consumption never gets eaten. And that kind of equates to approximately 10% of global emissions are associated with this food loss and waste. And this study focuses on food loss, not food waste. Some of you may know the distinction. I will go through it in a couple of slides' time. But just to give some further context, this is a graph from the WRI through their kind of food model, and it essentially tracks the various interventions that we could make in agriculture in order to achieve 2050 climate goals within that sector. And you can see that reducing food loss and waste is a key element of this. And the kind of scales that we're talking about have been kind of similar in scale to a lot of the work that the IPCC have done. So we're talking a substantial amount. So where does the SDGs fit in? For those who aren't familiar, these are a set of 17 goals that were agreed by the UN in 2016, I think, although they've kind of been in the pipeline a few years before that. And they're essentially a set of interrelated kind of ambitious goals that if we deliver on them by 2030 in most cases, will have done a decent job in moving the planet and its people and its inhabitants towards kind of a more sustainable future. And so, in the perspective of food loss, I focus on 3 SDGs in the context of food grain loss in India, and that is SDG 12, and specifically 12.3. I don't want to get too lost in the minutiae of this, but there is a specific target that calls for a clear reduction in food loss and waste. And there are similar targets for nutrition and the rates of malnutrition around the world. And we know that several hundred million people are either hungry or have some kind of malnutrition kind of effect. And that's not to say it doesn't have to be kind of visible hunger. It could be they're not getting enough protein, they're not getting enough iron or a kind of a mineral, or it may not be a visible kind of affliction. And finally, how does energy facilitate the reduction of food loss in order to provide better nutritional outcomes? So that's the motivation. And I said I'd kind of make the distinction between food loss and food waste. Well, this is a stylized kind of schematic, and essentially from the point of harvest all the way through to where food gets consumed, it goes through a number of stages. And food loss refers to the reduction in mass of any type of food between the point of harvest and the point just prior to sale, or just prior to kind of being put on the shelves, as it were. And that's kind of a measurable loss in mass, and it occurs throughout all these kind of stages. And food waste is anything from the point of retail. So, for example, if you had a bunch of wheat and some of it was left in the field because you couldn't harvest it and it rotted, that would be food loss. But if you threw away some bread because it went moldy on your house, that would be food waste. And we focus on the former, which is food loss. So what are the sources of food loss? Well, there's actually quite a few, but in terms of grain, the predominant ones are pests, various types of fungi and mold. Rats are a significant issue. And actually, if the grain is kept in kind of substandard or suboptimal conditions, it carries on its germination, and so actually you can have a loss of usable grain there just because the climatic conditions aren't suitable. And what are the underlying drivers? Again, there's quite a few, and they apply to different stages, but essentially they can be broken down into saying, well, there isn't the adequate machinery or the distribution or the kind of underlying system of whatever kind of food group you're in. The access to kind of modern energy services, which is what we focus on, and education and training of farmers, of practitioners, and also, which is quite a key one, is the access to capital in quite a lot of these situations. If you have nowhere to store your grain and you have to kind of sell it there and then, you're not as equipped to be able to kind of to take best advantage of these kind of various existing technologies if you simply don't have the funds to be able to do so. So why India? There are three main reasons. The first one being that the rates of malnutrition are severe, and the outcomes in particular for young children and women are even more so, and kind of among the most severe in much of the world, actually. The second point is that demographically it's very interesting. So it will soon become the most populous country in the world. Depending on where you look, it's any time in 2021 to 2027. But in the next few years, there will be kind of 1.4-ish billion people in a single country, and also to kind of supply the needs of those people, a lot of the infrastructure has yet to be built. So it's a rapidly kind of expanding country in that sense as well. And finally, and I know this kind of affects many studies, but actually looking at food loss data and looking at good quality food loss data, India is one of the few countries that you could get sub-national data for that isn't just kind of an aggregated level. And what I mean by that is, so the FAO has a number of food balance databases, and quite often, just for example, the data it contains, I saw a report that only about 4% of actual data observations are from an on-the-ground perspective, i.e. they've been surveyed, they're at a sub-national level, and the remainder is simply modeled at a macro level. And so there's no kind of intrinsic reason why that's bad. It just goes to show that actually a lot of these are done at a aggregated national level, and far, far, far fewer are actually an on the ground kind of bottom up approach. Okay, and why grain? So essentially because it is by far the largest contributor of calories in a typical diet. And you don't have to worry too much about the grains that we're going to look at, but these are the 5 major grains that are consumed. And this is kind of the nutritional profile of the 5 nutrients that we look at. And again, you don't worry about remembering all these things, but I just want to kind of point out that not all grains are created equal. They have got various different profiles, and it doesn't always tally up with where the policy instruments are in order to encourage or not the consumption of those grains. Okay, so at a high level, we've got approximately 65 million tons per year of total food losses across all food groups in India, of which grains is about 12 million tons. And when you take out sugarcane, which is actually the single largest source of food loss in India, if you take that out because actually it's nutritionally kind of nil, grains become the largest loss segment. And just a quick point, it may not look too substantial, 6% across all food groups, but remember that excludes the stuff that gets thrown away by households and at retail. And there's actually a huge amount of variation across food groups and actually across the country in these rates. So, and this just gives you a high level kind of distinction between the various grains and the rates within. And so we won't touch too much on this, but this goes back to why we chose India, because we were able to get subnational grain-specific data on the loss rates to inform the study. And you can see it's approximately 5%, but there are some kind of clear distinctions there. So this is an important point, because when we talk about food loss, it's important not to try and say that we've got a double win here. So there are 2 things that you can do. You can either reduce losses and then reduce the corresponding resource inputs and associated GHG emissions that would have gone into making those food that then was lost, or you can increase the nutritional supply, but your overall input of resources and GHG emissions stay the same, and you can't do both. So you can't win on both levels, but we select to study the second option because of the mentioned severe nutritional challenges in India. But just to give a bit of context, we also calculated at a very high level what you would save in terms of energy and CO2 equivalent emissions, and approximately 10 terawatt hours a year in useful energy and 13 megatons of CO2 equivalent. And these were kind of sourced from a previous study that we then applied. It's kind of the magnitude of losses to these previously kind of estimated rates. So that gives kind of the counterfactual what would happen if you reduced losses and reduced resource inputs. So now we're actually going to investigate what would happen if you reduced losses and then increased your nutritional supply. And so a very, very brief method. Essentially what we did was find food loss survey data, and there isn't too much of it about, but we got a data set from a Indian government institute that actually had sub-national, so you can see these regions in India here, these are agroclimatic zones. And so these aren't administrative in terms of states or districts. These are more like what the local climate is like. And so the loss rates were broken down by these zones and also broken down by the type of supply chain stage that these losses occurred at. And so then we combined this data with district level crop production data. And I'm fully aware that districts may mean different things to different people, but districts in India are basically in any given state or territory, there are a number of districts that make up that state. And I think there's approximately 700 districts. So we took crop data from these districts. We then mapped the districts onto the corresponding agroclimatic zone to kind of combine the loss rates with the magnitude of crop production data. And essentially, we do that for about 30 different crops at all stages of the supply chain for all districts, which is kind of a handy overall data set to have. And anyone that has spent time trying to kind of merge various bits of data knows that that took quite a long time. But we're only concerned for this study with 5 major grains that we talked about before. That's rice, wheat, maize, bajra, and sorghum. The first 3 will be familiar, the latter 2 may not be. And so how do we kind of attribute these food losses to the nutritional element? Well, we looked at the grain composition that you saw earlier. We looked at the recommended daily allowance of these different nutritional elements. And then we essentially tried to map how much of these total nutrients could be then additionally supplied to the Indian population based on their daily needs. And we looked at these five nutrients: calories, protein, iron, zinc, and vitamin A. Okay, and at a very, very high level, we found that approximately 40 million people could have their daily needs met of these 4 nutrients, vitamin A far less so. And I might speak about that at the end, but we can pause that for a while. So this is informative in the sense that we can get a total magnitude of people. And so it's about 4% of the total population could have their daily needs met. And we also calculated, okay, that's all well and good, but actually, can we focus on the nutrient deficient population and how much of their needs we can meet? And so we've estimated this as well. And I'm not going to show this here because I'm going to show those results in the PhD symposium in a couple of weeks' time, but that's kind of the next stage on. So 40 million people if we addressed grain losses. And so how do you address grain losses? So there's a number of ways, as I talked about before, of which we focus on one. So you could make the case that, okay, we need kind of training, or if we have a bunch of targeted funds, then farmers will be able to kind of invest, which is all true. But we wanted to specifically look at how energy plays a role in reducing losses in the storage component of grain. So this is quite a nice chart, really. And just for a bit of context, a lot of grain in India is stored like this. They call them caps or cover and plinth, and essentially means sacks of grain are stored on kind of raised beds and then covered with kind of sheets. And there's movement, there's political and policy movements in India to kind of move towards these modernized grain silos that have far lower rates of loss, and the quality of grain is kind of kept at a marketable rate. However, to do this, you need to control the climatic conditions inside. So we looked at sources of loss, but essentially it comes down to the fundamentals of temperature and moisture content of grain. So you may have read stuff about the need to improve kind of the cold chain of countries. So in terms of fruit and veg and animal produce. So grain isn't perishable in the same sense of these things. However, if it's kept at too high a temperature and too high a moisture content, then that leads to kind of the propagation of pests, of mold, and actually leads to the grain deteriorating at a fairly rapid rate. So we have to control the temperature, we have to control the moisture content. So that means cooling it and drying it before storage, and also a bit of and also trying to maintain these conditions for the length of storage. And so just to give you a bit of background, the moisture content of some grains at harvest can be anywhere up here, really. So 25% moisture content is fairly common. Some grains, some species, some harvest conditions may even be higher than that. And we have to dry it all the way down to approximately 12 or 13%. And so there are a few ways you can do that. You traditionally, what you would do is you would kind of spread the grain out on a sheet outside and let the sun do it, which is fairly cheap because it's using the power of the sun, but you're opening yourself up to losses there from rats, from birds, from other animals, essentially having their way with as much grain as they can possibly eat. So the silo option also reduces losses from birds and rodents, but we have to mechanically dry and cool the grain. So this is what we tried to assess, and we tried to quantify this for these 5 grains. And essentially we take sort of the fundamental physical characteristics of cooling and drying, and that's the sensible and the latent heat involved in these grains. And then we parameterized this model by looking at literature values for the typical harvest temperatures, typical storage conditions, right down to kind of the really nitty-gritty biophysical characteristics of the grain. And we put that all together to get a kind of a complete model. And then we ran an uncertainty analysis to kind of assess over these range of values what the likely intensity of energy input will be required for these grains. And so I just want to focus a little bit, because this graph here is an important part of the model. And this essentially says different grains have different energy requirements in order to remove water from the grain. And remember, we have to dry the grain, because otherwise, if it's too high of a moisture content, that basically creates the conditions for loss. And so there's 2 things to note: A, that grains have different curves, and B, as we dry the grain, so down towards storage moisture conditions of around 12%, actually it becomes incrementally more difficult. So for every percent that you dry, the next percent is more difficult. And so we feed these into the model to get grain-specific energy intensity rates that then we ran a Monte Carlo simulation on to get a kind of a range of values. So starting from right to left, this is maize, the purple is rice, the blue is sorghum, red is bajra, and yellowy orange is wheat. And the left is a lower intensity and the right is a higher intensity. And the units of this chart are kilowatt hours per ton. And so a couple of things to note. The reason why rice and maize are further to the right, so they have a higher intensity in order to kind of create these conditions where you can store them for long periods. And that's primarily a function of the fact that the literature suggests that they are harvested at a higher moisture content than other grains. And the fact that there's a broader peak compared to other grains is also a function of the fact that there was a wider range of literature values. So the range that we ran the model on was over a larger kind of spectrum than it was for the literature values for the other grains. And so how does this relate to actually something tangible and something we can kind of put a fairly coherent picture around? Well, we compared this with previous research that had given energy intensities for production. So remember, we're looking at storage, which is after production, and this is to prevent losses. So actually, when we combine the energy input to production, and that's kind of to do with the fact that you need fertilizer you might need to pump a load of water around, and that requires energy. So when we compare this production energy to the storage energy, we see that approximately 8 to 16% of the production energy is additionally required if we're going to minimize storage. And you can see there is a fair amount of uncertainty in there, and that's a reflection of the Monte Carlo simulation. And so what are the broad policy implications and the implications for the SDGs? Well, we didn't really focus on the political aspect of this, but India has something called the public distribution system, which is the biggest food subsidy program in the world. And it provides subsidized grain and a couple of other kind of key crops, I think, for approximately 160 million families. So that's a lot of people. It's subject to a lot of debate and critique, and there are calls for it to be reformed because it's a very expensive program and it may not be targeting the people that need it most, but it no doubt has had a positive impact in some cases. Because of the politicized nature of this, we basically propose the solution to say, okay, overhauling the public distribution system will probably lead to better, kind of more efficient structure and a system that will enable you to reduce losses. But in the meantime, something you can do now is to modernize your storage solutions. And that is something that they're doing, but at a fairly slow rate the last time I checked. And we provide evidence that basically says, okay, if you're going to do this silo kind of initiative in this program, these are the things that you need to think about, and this is what it will mean nutritionally, but also these are some of the inputs that you're going to need to consider. And actually, if India was to roll out and scale up this program, we kind of say you would need to have kind of a full engineering assessment of the energy requirements for kind of operating these kind of large, thousands of ton silos. From an SDG perspective, where this is one case study, and anyone looking at SDGs knows that there are a lot of targets, there's a lot of interactions, and there's a lot of unknowns. But we kind of make an explicit link between SDG 12.3 and a target in SDG 2, which correlates to the nutrition rates of a given country. And we make the argument that actually there's a synergy there between reducing losses and improving nutrition, but it's facilitated by another SDG, and that is in part, you need to provide modern energy services if you want to realize some of these benefits. And just a couple of concluding remarks, kind of takeaway: 40 million people could have their daily nutritional needs met of calories, protein, zinc, and iron if just grain losses were eliminated. And the energy to reduce the storage component of these losses is approximately 8 to 16%. A key limitation, which we always knew going into it, is that we didn't base the model on observed climatic data around India. So it's basically drawn from published literature and Indian government industry standards. The reason why we didn't focus on the climatic data to build the model was because of this disconnect between the optimum time to harvest and when they're actually harvested. Because we know that the moisture content is a key variable, and so, but we don't know exactly when and what time of day the crops may be harvested, and therefore what that correlates in terms of the moisture content. If that makes sense, I'm happy to kind of talk about that further. So actually thought it was more applicable to have stylized values than directly observed values. Future work, it would be really interesting to look at other food groups. So I said that grains weren't necessarily perishable, but there is an extension to the model which you could look at other food groups, so fruit and vegetables, some kinds of animal protein, but also different geographies. So India, because of its scale, has a large food loss problem, but its loss rates are actually lower compared to some of its neighbors and compared to other parts of the world. So applying this method to different geographies could be an interesting compare and contrast. And finally, and this motivates my research now, going through this study, we kind of realized that technical solutions exist, and we quantified aspects of a technical solution, but there has to be sort of social buy-in to some of the changes. So it requires a change of behavior on the part of farmers, on the part of distributors, but also if you're providing additional nutrient supply, people have to still choose that food and they still have to eat that food. And there's a lot of behavioral influence that goes on into diets, and there's a lot of kind of culturally significant aspects to that. And so that's what motivates my current studies, is kind of trying to build up this behavioral understanding of diets. And so that's the end of the kind of the formal study. But I did say I wanted to have a couple of minutes. How am I for time? We're sort of 40 odd minutes in. I wanted to kind of have a couple of minutes just to talk about IASA. So some of you may know it, some of you may not, but it's an institute based in Vienna, and it's formally called the International Institute for Applied Systems Analysis, which I was anecdotally informed kept things suitably vague, that they were free to pursue whatever research agenda they wished. But they run a program called the Young Scientist Summer Program that I was fortunate enough to go on last summer, and also our very own Yoga at CEP was also fortunate to go on. And essentially it's a 3-month funded fellowship where you kind of collaborate with other students from all around the world, and you work on a kind of a specific interdisciplinary project with an IASA academic. And so unfortunately, obviously this year it was postponed, but for any PhDs on, or any master's students thinking about PhDs and thinking about the future, I can highly recommend it. The application window is October to January. And I'm happy to kind of field any questions on this aspect as well. But just two other things. So a couple of background pieces that are fairly interesting. So over the past 50 years or so, it was initially set up as an initiative to kind of create bridges between East and West, specifically in the role of sharing and collaborating on science and academia. This was at the height of the Cold War. And anecdotally, again, we were informed that actually there was at least one case of espionage during the kind of years from the 70s into the 80s. But now it's repositioned itself to basically be a world-leading kind of hub that seeks to address 21st century challenges, but in a systems thinking approach. And it's got a real strength in modeling and underlying data. And they feed into a lot of the IPCC stuff and other kind of global assessments. And most importantly, there's a fairly good and structured social and networking program. It was a great experience. I highly recommend it to any first, second, or third, or fourth year PhDs. And as I say, I'm happy to field questions on this and happy to talk about my presentation. So thank you very much. Let's have a look. I'm not sure how this bit works, but if anyone wants to ask a question or type a question about anything, then I'm happy to field a few things.
Thanks very much, Matt. Yeah, I think people will either they can raise their hand on their next to their name, or they can type something in the chat, or they can just pipe up and ask a question.
Cool.
So, anyone got any questions?
Let's have a look. Mira, okay. No, that's a good point. So if anyone can see the chat, essentially looking at low carbon but small scale solutions. And yeah, this is something that we found, because actually quite a lot of produce is kept by the farmers. And so I don't have the exact percentages on the top of my head, but it's something like as much as between 30 and 50% of their produce is kept to themselves, and the rest is marketed on the wholesale market. And so there is a move to kind of improve the localized storage. There is a consideration that there may not be the service provision at that level, and I think the reason why there's sort of a large scale push is because of this public distribution system, which is a very large operation, and I think because there is a certain degree of centralization that goes on here, I think that's why there's a push for kind of large scale silos. But it's a good point, and I think I've seen a bit of research that does look at these kind of smaller scale solutions as well. Selective breeding in grains, reducing energy needs but maximizing nutritional benefits. Ooh, yeah, it's something that we didn't unfortunately have time to have a look at, but I can give a bit of background. So between the 60s and the 80s, India had a program called the Green Revolution, and that essentially was to kind of industrialize and mechanize their agricultural grain production, but really focusing on rice and wheat, and less so on other more nutritious grains. The exact reasons for that, I'm not too sure, but one reason is that the general push was productivity and yield, and basically overall provision, rather than the nutritional characteristics of the grain themselves. So rice and wheat has benefited from a huge kind of central push that actually means that over the years, the intake of these more nutritious grains have been going down. And we know that actually rice, in terms of grain, is like one of the most CO2 intensive, it's like the most water intensive, and nutritionally it's fairly poor. So that's something that needs to be looked at. I've seen some literature that is making the case that we need to diversify our grains, but I've not seen too much on the actual selective breeding. But that is certainly interesting. Cool. If anyone's got any more questions now, or if they want to ping me an email after on the actual research or on the EASA program, then very, very happy to kind of give further information on that. I guess over to you, Mark or Serena.
I think we've exhausted the questions. So I guess with that, just reminds to say thank you very much. It was a great presentation. I thought it was really interesting and well done. Pleasure. I look forward to seeing that final few slides you didn't show us.
Yeah, no, sure.
Thank you very much, and thanks everybody.
Thank you very much, everybody. Thank you.
Bye.
Bye. Bye.